We have a long but thick wire of radius r carrying a current I, and our goal in this video is to find the magnetic field inside the wire. Now in a previous video, we already did this, but we calculated for outside the wire, and we did that by using Ampere's circuital law. And when we simplified, we found the expression for the magnetic field outside to be this, mu naught I by 2 pi r. And for details, you can go back and check our previous video, but I wanna give you a very quick refresher of how we did it. We went to some point at a distance r outside the wire, and we realized that the magnetic field is in circles, and the magnetic field value is the same everywhere along that circle, its magnitude. And so we chose an Amperian loop, which is also a circle of radius r, and because of that, over the entire loop, B and dl are in the same direction, and B has the same value. And so when we simplified B dot dl, we just got B dl. And since B is a constant over the entire loop, its magnitude is a constant, we pulled the B outside the integral. And the integral of dl is just adding up all the dl's along that circle, giving us circumference, which is 2 pi r. And according to the law, that equals mu naught times the enclosed current. And to find the enclosed current, we attached a surface and found that the entire current I is being enclosed. And so we get this to be B times 2 pi r equals mu naught into I. And if we rearrange, we get this expression. But again, a full detailed version can be found in our previous video. But now we need to figure out what the magnetic field is inside the wire. So let me get rid of this. So this time, let's consider a point inside the wire. And again, let's say that the distance from here to that point, some point inside, is r. How do I find the magnetic field over here? Well, we can start similar to what we did over here. We look at what the magnetic field looks like, and just like outside, even inside, it should be in circles. Like, why would it be any different? Symmetry, right? So the magnetic field inside will also be in circles. So the magnetic field over there would also be a circle. So let's try and draw that. Here it goes. And according to our right-hand thumb rule, it's gonna be this way. And just like before, the magnetic field everywhere is a constant, and it's tangential to the circle, which means the Amperian loop that we're going to choose, just like before, should also be a circle. So here it goes. Here is our Amperian loop. This is also a circle. We'll also travel in the same direction. And if we now calculate what B dot dl in that closed loop is, what do you think we'll get now? Can you pause the video and think about this? All right, since B and dl are in the same direction and B is a constant everywhere, B dot dl becomes B dl, and B can be pulled out. Integral of dl gives you 2 pi r. Exactly the same thing as we got before. Absolutely no difference. I mean, why would there be difference? The geometry is exactly the same. So the left-hand side I'll directly write now is gonna be B times 2 pi r. 2 pi into r. No difference whatsoever. So maybe we get the same answer? Let's see. What will be the right-hand side? Well, right-hand side is mu naught times I enclosed. And again, what is I enclosed? You have to attach a surface, dip this, imagine dipping it into a soap solution, this loop. There will be a film that gets attached. Let's attach that. Here we go. And now the current that is penetrating through that surface, that becomes your I enclosed. The question is, what is that value? Is that the entire current I? Is I the I enclosed? Not really. Because think about it. Current I is the total current passing through this entire area. Let me show you what I mean. If I consider this entire area of radius r, then the total current that is passing through that entire area, that is I. But our area is less than that, right? Small r is less than that. So what we want to calculate, I enclosed, is the total current penetrating that area. And the question is, how much is that? Clearly, it has to be less than I, right? But how much? And how do we figure that out? Well, one assumption that we can do, and let me write that down over here, we can assume that current is uniformly distributed over the entire area. So let me write that. We can assume uniform current distribution. So we're assuming that per square meter or per centimeter square, whatever you want, the current will remain exactly the same, so uniform distribution. So given that we're dealing with uniform distribution, given you know that in this area the current is I, can you pause the video and think about how much will be the current through this much area? Can you pause and try? Okay, now I never used to understand how to do it when there were variables, but I felt my brain worked when there were numbers, easy numbers. So what I would just do is I would just take some random numbers. So let's say the current is, I don't know, 50 amperes, some nice numbers. Let's say this area is, I don't know, maybe 10 meters square. And let's say this area, which is a little bit less, I don't know, maybe it's 3 meters square. And our goal now is to find out how much current is passing over here. I know it's less than 50 amps, but how much? So how would I do this? Now I know. See, the first thing I'll do is calculate how much amperes I'm getting per meter square. So to do that, I will just divide the two. So 50 divided by 10. And so I know immediately, I'm getting 5 amperes for every meter square. For 3 meters square, I just multiply by 3. And that'll give me 15 amperes. And that's the answer, 15 amperes. Now, the answer is not important. I just look at this calculation, and now I think about, how did I do this? So I took the total current, and I divided by the total area. That gives me the current per area. And then I multiplied it by the area that is needed. That is this area. So if you didn't get this before, can you now try and figure out what that current is going to be? All right, so let's do that. So this current is going to be total current, I, divide by this area. That area is not R, R is the radius. What is the area? It's pi r squared. Pi r squared, let's write that, pi r squared. So this gives me the current amperes per meter square. And now if I want in this much area, I multiply it by this much area. So that is pi small r squared. So I get pi small r squared. And so notice pi cancels. And there we go. Now if I rearrange, I'll get my expression. So the magnetic field inside turns out to be, let me write this, mu naught I r square. Oh, 1 r cancels as well. Okay, so yeah, you just get 1 r divided by 2 pi r squared. So now let's digest this formula. What is this formula telling us? Well, it's saying that the magnetic field is proportional to the current, more magnetic field, very similar over outside as well. So that makes a lot of sense. But something interesting that you see now is that the small r is in the numerator, meaning as we go farther and farther away from the center, the magnetic field actually increases. Notice in the denominator, there is a capital R square, and capital R is a constant. It's the thickness of the wire. That does not change. So as I go farther and farther away, magnetic field starts increasing. Why is that happening? Because outside, the magnetic field starts decreasing. Why? Why is that? Well, think about it. As I go farther and farther away, clearly the length of the loop starts increasing. As you can see over here, 2 pi r starts increasing. But the loop will start enclosing more and more current. So your current will also start increasing. The enclosed current also starts increasing. And notice the enclosed current depends on r square, so that increases faster. And therefore it all nicely works out that you will finally see that the magnetic field starts increasing as you go farther and farther and farther away. So as I go from center magnetic field would be 0 because r is 0. So you start with 0. As you go farther and farther away, magnetic field starts increasing linearly because B is proportional to R. So if you draw a graph, it'll be a straight line. Please draw a graph, okay. We'll draw a graph, okay. So it'll be a straight line. Anyways, linear starts increasing, and then it'll reach a maximum. And then if I go outside, now I use this formula. I use this expression. And now you will see the magnetic field starts decreasing. And you may ask, why? Why is it that magnetic field decreases as I go farther away? Because once you come outside, now as you go farther away, the length of the loop increases. But now the total current enclosed stays the same, I. So this does not increase at all. And therefore now, as you go farther away, the magnetic field drops off as 1 over r. That's the story. And so the last thing I would encourage you to do is write this entire story in a graph. So let's do that. Let me do that somewhere over here. Let me make some space. All right, so if you were to draw a graph of magnetic field B versus the distance r, can you pause and think about what would that graph look like? All right, as long as we are inside the conductor, we will get a linear graph, B proportional to r. So we'll get a straight line and keep increasing. Until when? Until we are inside. But how do I represent that in the graph? Well, until the r value is equal to capital R. Because once r becomes more than capital R, I come outside. So this will be true until r value equals capital R. So r equals capital R. Now, once r value increases more than that, now I'm outside. And now I have to use this formula. And this is B decreases as 1 over r. It's no longer linear. You will get a decrease like this. Finally, if you're really, really curious, you may ask, Mahesh, what about when we are at r equals r? On the surface. We know it's a maximum, but which formula do I use? Do I use the formula for inside or do I use the formula for the outside? I would say you can use any one of them. In fact, both of them should give us the same answer. And you can check that. If I use a capital R, the capital R cancels and I get mu naught I by 2 pi r. If I substitute r over here, you get the same answer, mu naught I by 2 pi r. So on the surface, you get mu naught I by 2 pi capital R. And that, my dear friends, is the story of magnetic field due to long, thick conductor carrying currents.